of a point x is just the iterates of the dynamical system. So it's Tn of x, where n is some value in the natural numbers, although I also want to include 0. So it's just this set, and by Tn of x, I just mean T composed of itself n times. And so essentially the study of dynamical systems is looking at the properties of these orbits. Because you can, so this is discrete time. You can generalize this in several ways. For instance, we could start also looking into the past. So we could let n be an integer, particularly if map T is invertible. We can also, instead of looking at discrete time, look at continuous time, and then n would be some value in the real numbers, and we'd need a flow rather than a map. But for this talk, I will just stick to this discrete time setting and only looking into the future. Okay, so as I said, I want to look at how randomness can come in when looking at dynamical systems. And so we need a setting, so we need to take a choice of our space X. So we're going to take X to be, we're going to take X to be the circle. And what I mean here is, well, take the interval 0, 1. So just the interval going from 0 to 1, but then we're going to glue the point 0 to the point 1 to get a circle. So you have a point. So 0 and 1 become the same point when we glue them together, and that gives us a circle, which is often depicted as R mod Z. So this will be the space that we work on. Okay. I should just quickly explain what distance on the circle is. And basically, if you have points alpha and beta, I'm not going to define this formula, I'll just draw a picture. Well, there's two waves around the circle. There's one I'll draw in yellow, and there's the one I'll draw in red. And the distance now on the circle is just whichever is shorter. So you can either go clockwise round from alpha to beta, or we can go anti-clockwise, and we just take whichever is the smaller of the two, and that'll give us our distance. And this is always smaller than or equal to a half, because there'll always be one way round, which is quicker than when it's less than or equal to a half. So this is our setting for our first dynamical system. And what we're just going to look at is rotations on the circle. So let's introduce that. So we're going to take alpha to be some value in 0, a half, and we're going to assume that it's irrational. And we're going to define our map T from the circle to itself by T of x is equal to x plus alpha if x is smaller than 1 minus alpha, and it's going to be x plus alpha minus 1 if x is greater than or equal to 1 minus alpha. And so this is just simply a rotation on the circle by alpha. So if we started, if we look at the orbit of 0 and say alpha equal to 1 over root 2, I'll get set as a question. Okay, so or better still, let's take it as root 2 minus 1. Well, then we'd start with 0 would be the first point, which would just be 0 itself. Then you'd rotate to root 2 minus 1. Then you'd rotate to 2 root 2 minus 1. So we'd be getting points, say, here, then round here. But then the next time we'd be at 3 root 2 minus 1, and we'd go back past 0. And so at this point, we need to subtract 1. So it'd be round here somewhere, and then we'd keep on rotating. So that's our circle. So that would be our circle rotation. Okay, so now I want to talk about relating this to randomness. Okay. So connections to randomness. Well, our first question about how it connects to randomness, take an interval, so I somewhere contained in the circle, does an orbit eventually, so however we choose the interval, does an orbit always eventually hit the interval I? This is the property often referred to as denseness of orbits. So here we have our circle, again with 0 equal to 1, and then somewhere I'm going to draw a Yarrow interval. If we consider an orbit under our system, will it always eventually hit the Yarrow interval? Okay, so the answer is yes. Now I'll try and demonstrate why it's true, just for the case where we consider the orbit starting at alpha. So these would be the points alpha, t of alpha, which would in this case would be 2 alpha, and then t squared. So t squared of alpha, which would be 3 alpha, but then when you might need, if it goes past 1, you might need to subtract 1 to reduce it back to the circle. So t squared is equal to 3 alpha, and you often denote this reducing it back to the circle by putting curly brackets around. So t squared of alpha would be 3 alpha reduced back to the circle, t cubed of alpha, and so on. So this is our orbit. We want to see whether it will eventually hit any interval on the circle. Okay. So how can we show this? So here's our point 0 is equal to 1. we've got some value alpha, and let's just start applying elements of the orbit. So going round to 2 alpha, round to 3 alpha, 4 alpha, and so on. And eventually, we'll come round to the other side of 0. So we have a value k alpha, which occurs before 0, and then k plus 1 alpha, which is back beyond 0. So you don't have to subtract 1 to reduce the value mod 1. Okay, so how big would an interval, so how big would our interval I need to be so that we know that the orbit would definitely hit it at this point? So we've done this first k plus 1 terms in the orbit. How big would the interval need to be in order that we can guarantee that something will hit?
Does it need to be of size alpha?
Yes, exactly. So any interval of size alpha or above is definitely going to hit one of these terms, alpha, 2 alpha, 3 alpha or such, because they're spaced. The spacing between them is alpha until we get round to 0, and then it's rest of alpha. So any interval where the size is greater than or equal to alpha would definitely get one term of this, at least one term of this orbit hitting it. Okay, so we're done if, let's say, the length of the interval I is greater than or equal to alpha. Okay, now let's look at k alpha and k plus 1 alpha minus 1. So these are the 2 points either side of 0. Okay, so one of these is distance at most alpha over 2 from 0, because they can't, we know that they're both within alpha of 0, because otherwise they wouldn't have 0 between them, because the gap between k alpha and k plus 1 alpha is just alpha. So we know that they're both at most alpha away from 0, but then they're either side of 0. The gap between them is alpha. So one of these 2 distances, which I'll put in blue, must be smaller than alpha over 2. Okay, so now we rotate. But rather than rotating at one go at a time, well, let's say, in this case, let's say k is closer to, is the one which is within a half of 0. So rather than rotating by alpha, we now rotate by k alpha. So we jump terms on this orbit. But then we do the same trick. So we go round just beyond 0, and in this case now that would be going anti-clockwise, so it would go 0 to k of alpha, then we'd go to 2k alpha, keep going, but eventually we'd end up on the other side of 0. So we'd get the same thing with 2 points straddling 0, but now we hit, doing this, we hit any interval where the length of I is greater than or equal to alpha over 2. Because now these red terms are apart by alpha over 2. We now repeat the same trick to get alpha over 4, and then we'll do alpha over 8, and eventually, however small the interval is, we must enter that interval. So that is how we can show that our orbit, starting at alpha, is going to enter any interval. And there's nothing particular about starting at alpha. The same argument works wherever you start the orbit. You just, rather than you do the same thing, you don't need to ask which side of 0 you're on. You could ask which side of the starting point of the orbit you're on. So this way, we can show that this connection to random, so for this irrational rotation, the orbit is going to hit any interval eventually. Okay, just, are there any questions here? Okay, so that is one notion of randomness. Now, a more refined question. Which could be frequency of visits. And in fact, you can say more than hitting these intervals, always hitting these intervals, you can, in terms of a limit, say how often they will. So if I take, if I is the interval contained in the circle, then if I look at 1 over n and the number of times that Tn of x is in the interval I, and take the limit as n tends to infinity of this, then this will give the length of the interval I. And that's what's called equidistribution. And this holds whatever starting value you choose on the circle. So the number of times an interval is hit by an orbit is determined by the length of the interval. So in that case, our circle rotation is generating some sort of randomness. We start at a point, it's going everywhere in the circle, and in fact, it's visiting each interval. How often it visits the interval is just determined by the size of the interval. Okay, I'm not going to show how that's a bit more involved to prove and wouldn't work for a lecture like this. Maybe I'll mention, if you want to see how to do this, the thing you want to look up is Bayes' criteria, and it's an argument essentially using Fourier series. Okay, so that's equidistribution. But now I want to show a sense in which circle rotations are not so random. Okay, so still in the same setting. So consider, say, our set J n, which is going to just be the first n terms of the orbit of alpha. And again, and I'm using these brackets to indicate going back to the circle. So what's called reducing things mod 1. So we have this value, it's alpha to alpha up to n alpha. So now, if we look at where they are on the circle, so we're going round with alpha, 2 alpha, 3 alpha, 4 alpha, and let's say here alpha is something between 1/7 and a 6, so 7 alpha is back beyond 0. So if we look at how they're distributed. And if we look at the gaps between digits, well, there's only 3 possibilities. There's the gaps, there's alpha, for example, between alpha and 2 alpha, the distance is just alpha. And that's going to the whole way around until we get to 7 alpha. And then there's the gap between, there's whatever the distance between alpha and 7 alpha is. Which is this gap. Which is this gap here. And then if we rotated once more, we'd get 8 alpha, and now we'd have a third distance. We'd also get the distance between alpha and 8 alpha. Notice that if we look at 2 alpha and 8 alpha, that's just the same as the distance between alpha and 7 alpha. So we get this point, so we get 3 distinct gaps. And now, despite the fact that we saw the circle is nicely distributed, it hits any interval and it actually hits it with a given frequency. However large we take n, there are no more than 3 gaps. So these are, so when I'm talking about gaps, I'm not taking the, ignoring the order in the set Jn, but just looking at the closest points, so the distance between neighboring points for the points in Jn. So however large we take n, we never get more than 3 possible values for the gaps between points. And so in this, so we saw with hitting any, that it hits any given interval, but in this sense, really the circle rotations are not generating sets which are very random at all, because there's very few possibilities for the different gaps between them. So now let's give an argument of how you can show this. So this is sometimes called the free gap theorem. Okay, so and let's write Jn again. So we've got these values, alpha up to n alpha. Okay, so now we're going to suppose that m1 alpha and m2 alpha are neighbors. So there's no points in the set between them. So if we go around a circle 0, so there's somewhere I say m1 alpha is here and m2 alpha is there, and the neighboring points, so there's no other point in the set between the two, and m1 and m2 are less than or equal to n. So the gap between these will be one of the gaps. Okay. So now, what happens with M2 plus 1 alpha and still reducing things back to 0 and 1 and M1 plus 1 alpha? Okay. So under what circumstances, if we have neighbors M1 alpha and M2 alpha, under what circumstances are M1 plus 1 alpha and M2 plus 1 alpha, they're not also neighbors?
Is it something when, say, M2 is N or something like that? So it goes around the edge.
Yeah, exactly. So they're not neighbors. So one case is either M1 or M2 is N, in which case when you add 1, you get something which is not N. And then because alpha is irrational, it can't be a value which previously occurs in Jn. So in that case, they wouldn't be neighbors. How else, is there any other way you could get that they're not still neighbors?
Well, they can't be the same value, can they, to start with? Because then
they're not.
So
they can't be the same. Okay, so we've got M1 alpha, M2 alpha neighbors. Now, if M1, M2 are both Rasterman, well, then let's look at M1 minus 1 alpha and M2 minus 1 alpha. Now suppose they're not neighbors, then we can find a red point between them, which is K alpha for some value of K. But if K is greater than 1, then when we go back to M1 alpha and M2 alpha, then we're going to have K minus 1 alpha between the two. And so in this case, M1 alpha and M2 alpha could not be neighbors, which would mess up with our original assumption. So if alpha is, so if K is greater than 1, this is not possible. So what we must have is K is equal to 1. And this means that M1 alpha and M2 alpha are either side of 0. So what we're getting, we've got 0, here's M1 alpha, here's M2 alpha. So at the moment, they're neighbors, but then when we rotate by alpha, M1 plus 1 alpha and M2 plus 1 alpha, we now get the orbit value alpha comes between them and they're no longer neighbors. So those are the two ways that if we have a pair of neighbors, then if you add 1 to both of them, we no longer get two neighbors. Either one of M1 or M2 is n, or they're either side of 0. So the way we prove the theorem is we take neighbors M1 alpha and M2 alpha and keep adding 1 until we no longer have neighbors. And notice adding 1 doesn't change anything to the gap because we're adding alpha to both. And so however many times we do this, we'll eventually end up at one of our cases when the cases. So either M1 or M2 will end up as n, or will end up either side of 0. And that is where, so the 3 gaps are the 2 gaps involving this last term alpha n. So the gaps come from the closest point to alpha n on either side. And the gap which contains 0. And these give us 3 possible values for the gaps, and there can be no more than 3. So this is the 3 gap theorem, which shows that things coming from irrational rotation, the orbits really aren't that random, because in terms of the gaps between them, it's very limited. Okay, are there any questions here?
I don't think so, no.
Okay, so let's think about some other dynamical systems. So generating randomness using a dynamical system. And actually, what we've been doing so far, and we've just been looking at an individual orbit, isn't really what you want. Because you don't really, if you take a point and then iterate the map several times, we don't know which values in the orbit to look at, and also we wouldn't know which point to start with. What we'd really want is, so here we've got a dynamical system back to a general one, so t from x to x. So what you want is a set A, some starting set A, which contains an x, and a pry t to A. And then what we want to get then is that Tn of A becomes increasingly random, whatever that means. So this is really what we want in order to have a dynamical system which generates randomness. So we have a map from X to X, we're given some set A containing an X, and if we keep on applying T to A, then it becomes increasingly randomly distributed. Okay, so now let's try and state this in terms of a practical problem. So here is some dough and some dried fruit.
I think for this section, it might be more effective if you stopped presenting your screen just quickly, but it means a big thing on everyone's screen. Thank you.
Okay, so here is a dough and some dried fruit. And so what we want is some process in which, if we keep applying it to the dough, the dried fruit ends up being evenly distributed throughout the dough. So this would be our aim in generating randomness through a dynamical system. So we might want, and so our process, can you see me if I'm here? Or maybe I've been to table a bit.
Yeah, that's pretty good.
So a process could be where we squash down. So we're squashing down in one direction because this is then expanding in the other directions, but then fold over. Hopefully not making too much of a mess of my office. So we fold over in one, then fold over in the other. So this would be our first iteration of our map. And then we squash down again. So squashing down, expanding, and then fold over once, and then twice, and then repeat the process, squashing down. Maybe I'll put some of the fruit back in. So again, we squash down and fold over and fold in the other direction, and then squash again. And fold in both directions. So this squashing and folding process. And if it's doing what it should, the fruit is getting distributed evenly throughout the dough. So, and this is exactly the sort of randomness that certain dynamical systems create. So let's okay, so what I'll do is go back to screen sharing. Okay, and so first of all, so I want to finish with two things. So what do we want this dynamical system to satisfy? And this property is mixing. So if we have A, which is the dried fruit, and B, which is just some subset of X, if we apply the dynamical system enough time, we want there to be a reasonable proportion of the dried fruit in the set B. So to look at that, we want to look at the set B So we're calling our map T from X to X. X would just be our space of the dough and fruit combined. So then we have B intersected with T to the minus N of A. So these would be the points we show in B, but these points have started off the dried fruit, but they've ended up, once we've iterated the map, A so we want points which start off as dried fruit, but if we iterate them n times, end up in the set B. And by that, we have T to the minus N of B. So T to the minus N of B is just points X, where T of N of X is in B. Okay, and we want these to be evenly distributed. So let's think of volume, and suppose the volume of X is equal to 1. So then we want the volume of A intersected with T minus N of B. So we want the amount of fruit in the set B to be based on the proportion of dried fruit to start with. So that should be the volume of A, which is the proportion of dried fruit to start with, multiplied by the volume of B. So this is what we'd want to happen for it to be evenly distributed. But if we want this to happen in finite time, it's going to be a struggle. So we need to take, if we want any chance of it happening, we want it to happen as a limit. So essentially, to get mixing, we'd want this limit then tends to infinity, the volume of A intersected with T to the minus N of B being equal to the volume A multiplied by the volume of B. And this is the concept of mixing. And it would normally be termed in terms of for essentially sets where it makes sense to talk about a volume. So for all reasonable sets, A, B contained in X. So that's the concept of mixing, and it's what we want for our action with the dough and the dried fruit. Okay, so that's mixing. Now, what does our map, which we were applying to the dough, look like? How can we model it? So I'm going to take our dough, which is almost a cube, so I'll take it as a unit cube. And so how can we model our map? Well, the first thing we did was contracted in one direction. So we take Z in the high direction, take it to Z over 4, and then we expanded in the other two directions. So to keep things simple, we have 2x, 2y, and Z over 4. So of course, that's now no longer contained inside the unit cube. To get back to there, we then needed to fold. So how did the folding work? Well, if X and Y are less than a half, then in fact, you squash down, you're still 2x and 2y will still be between 0 and 1. And so, in fact, in this case, we've not done anything more. So we just have 2x, 2y, z over 4. But now, suppose the x direction is greater than a half, but the y direction is less than a half. So now we've got x going to 2x, which is now greater than 1, so it's some value between 1 and 2. So now we're going to take 2 minus 2x. The y is less than a half, so that's going to stay the same, stay as 2y. And then the z direction, well, that is getting folded over to the top, so that's going to go to a half minus z over 4. Then if x is greater than a half and y is greater than a half, but then we're folding, then the folds in both directions are acting, so we're going to get 2 minus 2x, 2 minus 2y, and then we're trying to fold twice into z direction, so we're now going to get a half plus z over 4. And then to complete our Baker's map, we have the case when missing where x is less than or equal to a half, but y is greater than a half. So now the fold is just at hitting the y direction. So here we're going to get 2x, 2 minus 2y, and then we're going to fold all the way to the top. So we get 1 minus z over 4 for the for the height. So this gives us our Baker's map, which roughly is trying to mimic the process you do if you were, say, mixing, as I was, mixing fruit into dough. So this contracting and expanding thing. And in fact, it is possible to show that this Baker's map is mixing, the definition I gave before. And in fact, this is a standard example of a dynamical system which does give a lot of randomness. And this is the dynamical system where you see that it can be split into expanding directions and contracting. And so here you've got 2 expanding directions where distance is getting multiplied by 2, and you've got 1 contracting direction in the z direction. So this is what's called a hyperbolic dynamical system. And this is a dynamical system where you have expanding directions and contracting directions. And these are the dynamical systems which do show a lot of randomness in particular. And so not only will they be mixing, they'll also typically be mixing with relatively quickly. Okay, then I've gone for about 50 minutes, so I think I should stop there.
Cool, that was really interesting. Thank you. Does anybody have any questions? Let's see. Okay, I don't believe so. I have a quick question though. So obviously with the dough folding, it's a little bit arbitrary, or not arbitrary, but it's a little bit inaccurate really, because things like the dried fruit falls out, etc., and the fold perfect. But generally speaking, do you think that the hyperbolic dynamical system would be able to, perhaps if you knew the starting conditions, you would be able to predict exactly what was going to happen, provided that the sort of our function here is being applied perfectly each time, or it's sort of like really unstable, that if the function is applied even slightly incorrectly, the entire dynamical system becomes completely different after.
Yeah, also you need, I mean, in order to be able to say what's happening at time n for a point, you need to know exactly where the point is, because any set, however small it is eventually getting distributed throughout the space.
Yes, okay, and because they're all real coordinates, you're going to have a really big problem.
So if you have made it, so if your small error is, so if your starting point is a little bit away from where you were hoping it would be, the behavior for that point can be completely different to the point that's nearby it.
Yeah, so you can't use smoothness properties particularly, or anything like them, because even if it moves a tiny little bit, then where it will end up after n iterations for a large number of n will be wildly.
Yeah,
okay, that makes sense.
Yeah, while the map is continuous, the epsilons and deltas in the continuity will change with n, and so as n gets larger, the delta for a fixed epsilon, the delta you need to take just gets smaller and smaller.
Okay, yeah. Cool, that makes sense. Thank you.
I also have a quick question. So the randomness here is different from the randomness in a statistics sense, right?
So in a sense it is, but actually if you were studying systems like the Baker's map, so in statistics, have you seen the central limit theorem?
Yes.
So you would get an analog of the central limits theorem for the Baker's map.
Okay.
So while these systems are completely deterministic, you can get results which mimic the results you see in statistics.
Yeah. So like, even if there is randomness, the whole process is still deterministic, it's not stochastic.
Yeah, I mean, if I wrote it down as this, yes, the whole process would be deterministic, but you can write questions in terms of the measures on the system, which in this case I was talking about was basically the volume, and you could ask the volume of points satisfying a certain condition, then these would behave very much like random variables from statistics.
Okay. Thank you.
Is my interpretation then correct that there's almost so much, I'm not sure if this is the right place to put the words chaos theory, but there's so much chaos going on in this that in reality it behaves almost like random variables? Yeah,
so I mean, hyperbolic dynamical system essentially are examples of chaotic. I mean, I'm using the term hyperbolic because it has a clearer mathematical meaning, whereas chaos is not particularly well defined. But hyperbolic dynamical systems are essentially examples of chaotic dynamical systems.
Okay, cool. Thank you. Does anybody else have a question? If not, then perhaps we could wrap up here. Cool, I'll take that as a no. So Tom, would you like to stop the recording?
Yes, indeed.
Okay, excellent. Well, thank you very much, Thomas, for coming and speaking to us. It was lovely to have